Okay, so now we're going to talk about turbulent flows with respect to boundary layers and with flat plates because that's what we do a lot of our experiments with boundary layers on and simulations. So we know that boundary layers grow as we move along a plate. So let's draw a boundary layer here. Hopefully at this point you've drawn enough of them that you can kind of estimate the way it grows. Kind of slows down as it moves farther down the plate. The growth slows. And this is our delta x. It's our height. It's a function of x. It increases. We know that after the flow leaves, it has a velocity profile of some kind, right? And our goal for what we're going to do today is we're going to try to develop similar tools that we had to laminar flow on flat plates. So we want to be able to calculate the drag mostly. But for doing it for turbulent flow, it's much more complicated because we don't have an analytical solution for the velocity profile. So we're going to have to be a little bit more creative, and we're going to have to use our conservation of linear momentum tools that we've developed before. So what we're going to do is we're going to, and we've done this actually in one of your homework problems, we're going to pick a streamline that moves up and eventually merges with the boundary layer right there. And we know that this streamline has to move up because as this fluid slows down, remember, it spreads out due to conservation of mass. So this streamline will move up, but it will merge with our boundary layer right there. This is also a good time to note that boundary layers are not streamlines. So streamlines cross boundary layers. Yeah, that's important to note. And we'll draw our control volume around like this. And this control volume is going to have a force on it. And that force is going to be the shear stress that's being exerted on the fluid by the plate, which is in this direction like this. Because we're not including the plate in this, we're doing just above the plate. So we're going to use conservation of mass, where conservation of mass tells us capital U times h, which is the amount of fluid coming in. Remember, there's a unit depth into the page, so this is technically times a 1, but that drops out. It's going to be equal to the integral of 0 to delta of u dy evaluated here at the end. And so this helps us figure out what our delta is as a function of y, because however long we want to integrate, or wherever we want to pick in the x direction, this is x, this is y, we can stop, do this integral, and figure out what our delta has to be in order to be equal to this amount right here. But if we're going to do conservation of mass, or conservation of momentum, then our sum of the forces in the x direction will be equal to negative integral of tau at the wall times dA integrated over the plate. And that's going to be equal to negative b times the integral of tau at the wall dx. We're going to simplify our integral a little bit, knowing that it's unit depth into the page. It's basically equal to 1. And that's going to be equal to our momentum part of our equation, where we integrated our flow in and our flow out, right? So flow in is negative rho u squared times h times b, where b is our depth into the page and h is the height at the beginning. So this is our momentum entering our control volume. And then we add rho the integral from 0 to delta of u squared dy. And if we simplify this, it becomes equal to negative rho b integral from 0 to delta of u capital U minus lowercase u dy. And this represents the loss of momentum due to shear stress. Remember, momentum is conserved. If we lose momentum, it has to be because there's or gain momentum, it has to be because there's a force on our system. All right, so what we can do now is we can estimate our u here, our lowercase u. We can guess it, simulate it, or measure it, and plug that into this equation, and then get an expression for our shear stress at that point. We're not going to go into all the different ways you can model the average flow of turbulent flow, but what the result is that we can derive some drag coefficients and some skin friction coefficients. So our drag coefficient is equal to 1.328 divided by Reynolds number to the 1/2. And remember, this is for laminar flow. Now, as we increase our Reynolds number, we find out that this correlation changes to a fitted correlation, which is not nearly as neat. We get 0.455 divided by log of the Reynolds number. And the log is raised to 2.58. And we subtract 1700 divided by the Reynolds number. And this is transitional. So this is if our plate extends into that transitional flow. Remember, all of these drag coefficients start from the beginning of the plate. So this includes from the beginning of the plate to the transitional flow. And we can extend our distance down the plate, because remember, our Reynolds number, whenever we calculate these things, is our characteristic length is our length down the plate. So going down the plate effectively increases our Reynolds number. So if we increase our Reynolds number, we see that CDF is equal to 0.455 divided by log of Reynolds number L raised to the 2.58. And what's really happened here, by the way, is this is turbulent flow. And this is transitional flow. And what we've done is we've subtracted some of the drag coefficient due to the laminar flow that's occurring. And if you get a high enough Reynolds number, basically this doesn't matter anymore. Because remember, as Reynolds number rises, as you get more turbulent, Reynolds number rises. And so 1700 divided by your Reynolds number becomes a small value, and you don't need it anymore. It just drops away. So that's why this looks like this. And then CDF is equal to, it gets a little complicated here, 1.89 minus 1.62 times the log of E over L. Remember our old friend roughness? Yep, they're back. Raised to the negative 2.5. And this is completely turbulent. And that's analogous to, remember, you notice there's no Reynolds number in this expression here. And the reason there's no Reynolds number is because just like with pipe flow, once we reach a certain point, the drag coefficient, which is similar to the friction coefficient, but the drag coefficient is independent of Reynolds number and only a function of E over L. And we can see that if we go to basically the flat plate equivalent of a Moody chart. So looking at this picture here, we can see the completely turbulent region has straight lines that are only a function, or our drag coefficient is only a function of our E over L, our relative roughness, right? And then there's a complex region where we have this region here is relatively complex and hard to develop an analytical model for and to fit to. But we do have a model for our turbulent smooth plate, which is right here. That's this equation right here. And then as we move farther down on this plot, we see that the transitional flow, that's this right here we have a model for, and we have a model for the laminar flow. And those show up here and here. So we have models for this region, this line, and this region here, but we don't have any models for this region. It's kind of like no man's land. We have to use plots or do the experiments ourselves. Yeah. So in our next video, we're going to revisit an old problem, which is we're going to hook a banner to our vehicle, and we want to know what the force is on the pole holding the banner. And our banner's going to be big enough, and we're going to be moving fast enough now that it's turbulent flow.